Welcome to Shri Learning Academy. Let's simplify round robin scheduling algorithm. Have you ever been to an amusement park where you get unlimited food and ice creams? There is just one simple rule at the ice cream counter. You can take as many ice creams as you want, but only one at a time. If you want another, you have to go back, stand in the queue again, and wait for your turn. Now imagine many people standing in that queue. Everyone keeps moving forward one by one, getting their turn again and again. No one is allowed to stay at the counter for too long, and no one is completely ignored. The simple system ensures fairness and keeps the line moving smoothly. This is exactly how round robin scheduling works inside an operating system. Imagine a system where multiple users are trying to get attention at the same time. And instead of making anyone wait too long, everyone gets a fair turn again and again. That is exactly the idea behind round robin scheduling. It is one of the most practical and widely used CPU scheduling algorithms, especially in time sharing systems where responsiveness matters more than finishing one job as quickly as possible. Instead of letting one process run until it finishes or blocks, the CPU is shared in small pieces, almost like giving each process a quick chance to speak before moving to the next. This creates a smooth and fair experience, especially when many processes are active at the same time. To understand how this works, think of a circular queue. Processes are arranged in a loop, and the CPU keeps moving from one process to the next in order. Each process gets a fixed amount of CPU time, which we call the time quantum. This time quantum is the heart of round robin scheduling. It defines how long a process is allowed to run before the CPU moves on to the next one. If a process finishes before its time quantum ends, that is great. The CPU simply moves ahead. But if it still has work left when its time quantum expires, it is paused and placed at the end of the queue. This cycle continues again and again, giving each process a fair share of CPU time. Now let's make this more concrete with a simple example. Suppose we have three processes, P1, P2, and P3. Let's say each process needs 5 units of CPU time, and the time quantum is set to 2 units. The CPU will first run P1 for 2 units. Since P1 still has work left, it goes to the back of the queue. Then P2 runs for 2 units, followed by P3 for 2 units. After that, the cycle repeats. P1 gets another 2 units, then P2, then P3, and so on. Eventually, all processes complete. The key thing to notice is that no process has to wait too long before getting CPU time again. This improves responsiveness, especially for interactive systems like terminals or applications where users expect quick feedback. At this point, it is important to connect this idea with something you already understand from earlier topics. When we discussed context switching, we learned how the CPU switches from one process to another. Round robin scheduling relies heavily on context switching. Every time the time quantum expires, the operating system performs a context switch, saving the current state of the running process and loading the next one. This switching happens very fast, but it is not free. It takes time and resources. So, while round robin improves fairness, it also introduces overhead due to frequent switching. This brings us to a very important question. How do we choose the right time quantum? If the time quantum is too large, round robin starts behaving like FCFS scheduling. One process will run for a long time before others get a chance, which reduces responsiveness. On the other hand, if the time quantum is too small, the CPU will spend more time switching between processes than actually executing them. This increases overhead and reduces efficiency. So, choosing the right time quantum is a balance. It should be small enough to ensure responsiveness, but large enough to minimize unnecessary context switching. Let's take another example to see how time quantum affects behavior. Imagine a system where the time quantum is 1 unit. If there are 10 processes, the CPU will keep switching after every single unit. This means a lot of context switching. Now imagine the time quantum is 10 units. In this case, each process runs longer, but others may have to wait more. In real systems, the time quantum is usually chosen based on system performance and workload. It is often in the range of a few milliseconds. One of the biggest advantages of round robin scheduling is fairness. Every process gets an equal share of CPU time. Unlike priority scheduling, where low priority processes may suffer from starvation, round robin ensures that no process is completely ignored. This makes it very suitable for systems where multiple users or tasks need equal attention. For example, in a multi user system where several users are connected through terminals, round robin ensures that each user feels like they are getting continuous access to the system. Another important benefit is improved response time. Since each process gets CPU time regularly, even long processes start executing early. This is very different from algorithms like SJF, where longer processes might have to wait a long time before getting CPU access. In round robin, even if a process is large, it still gets a chance to run in each cycle. This is especially useful in interactive environments where quick response matters more than total execution time. However, round robin is not perfect. One limitation is that it does not consider process priority or burst time. All processes are treated equally, even if some are more important or shorter than others. This can sometimes lead to inefficiencies. Also, as we discussed, frequent context switching can reduce overall system performance if not managed properly. So, while round robin is simple and fair, it may not always be the most efficient choice for all types of workloads. To connect this with the broader picture of CPU scheduling, round robin is often used in combination with other techniques. For example, in more advanced scheduling systems like multi level feedback queue, round robin is used at different levels with different time quanta. This allows the system to balance fairness, efficiency, and responsiveness. You will explore this idea more deeply in upcoming topics. If you step back and think about it, round robin reflects a very practical philosophy. Instead of trying to be perfect or optimal for every single process, it focuses on fairness and responsiveness. It ensures that every process gets attention regularly, which is exactly what modern interactive systems need. Whether you are typing, browsing, or running multiple applications, this approach helps create a smooth and responsive experience. That is it for this video. See you in the next one.